the hardness of the martensite produced on quenching is a function of the amount of carbon which is present in the martensite. You can see here that suppose I plot hardness in RC scale, you see that with increasing carbon percentage, the hardness of the martensite increases. Parallelly, we had pointed out that though the hardness increases, but also so does the ductility decrease, and high carbon martensite may not be useful for practical applications. So, what we need to do is we need to temper this martensite, so that we have a good combination of ductility and strength. So, here in this table below are listed properties of 0.8% carbon steel. Now, sometimes you may come across a question that what is the, say for instance, the tensile strength or hardness of 0.8% carbon steel. From this table below you can see that this is not a well posed question, because of the reason that depending on the amount of first thing, of course, the properties depend on the percentage of carbon, definitely yes, but further it depends on the kind of microstructure you produce, or in other words the kind of heat treatment you give to produce a specified microstructure. Now, coarse pearlite has a hardness of about 16 RC, fine pearlite is even harder, about 30 RC, bainite is even harder, about 45 RC, martensite is extremely hard, but as I pointed out it is brittle, and therefore, often it is difficult to do find the tensile strength, as the specimen may break while doing the testing. Therefore, when you temper martensite, typically about 250 degrees Celsius, the hardness falls a little bit, but in bargain you can actually get a combination of ductility and strength. Therefore, now you understand that not only the structure, the composition determine the properties, but also the microstructure, and a direct handle on the microstructure is what we call by heat treatments. So, let me summarize this slide once more, because it is a very important slide telling that the composition is important, that the hardness of the martensite produced is increasing with the percentage of carbon, but more so if you compare even for a single composition like 0.8% plain carbon steel, the hardness can vary depending on the kind of microstructure you produce, the kind of micro constituent, and even within a single micro constant like pearlite. Suppose I am comparing two kinds of pearlite, fine and coarse pearlite. So, this is, say for instance, schematically I show here coarse pearlite here, and on the other hand suppose I have fine pearlite here. The hardness of these two and correspondingly the tensile strength etc. are different, because these have hardness and tensile strength are microstructure dependent properties. So, this is a very important slide, and all students of material science should keep this important point in view, that depending on the microstructure, the hardness and all the other structure sensitive properties will change. In this slide here, we have an overview of all kind of heat treatments, and when you are trying to change the properties of material, as I told you, you can get a handle on the microstructure by doing these heat treatments. But the general superset is that we can have either thermal treatments, which are called heat treatments, or you can have thermomechanical treatments. So, in thermomechanical treatments, not only do you apply heat, but you also may additionally work the specimen along with maybe work it at high temperatures, so that you can get a certain microstructure which is very desired for the properties. So, here is a broad listing of all the heat treatments that you can envisage. There may be more, but this is a reasonably broad overview. Heat treatments that only affect the bulk are given on the left, and heat treatments that means the heat treatments which affect the entire bulk are given on the left, and those which are essentially targeted at the surface are given on the right. Cut my slide. The bulk treatments that you can envisage are annealing, normalizing, hardening and tempering, mar-tempering and os-tempering. This is of course with special reference to steels, but we will see that there are more kind of treatments which we will encounter in context of aluminum alloys, and also other kind of treatments which we will not be covering in the current course. Then some of these names are familiar to us, like normalizing, hardening, tempering, but there are two additional terms like mar-tempering and os-tempering, which we shall take up very soon. In annealing, we have full annealing, recrystallization annealing, stress relief annealing and spheroidization annealing. We will briefly deal with some of these details of these processes, and the student may actually refer to a good text on heat treatment to understand the details. Here the focus being on the fact that you can actually engineer the microstructure by doing heat treatment. That means not only are you having a good understanding of the crystal structure and therefore the resulting properties, but also a handle on the microstructure. For surface treatments, there can be thermal surface treatments like flame hardening, induction hardening, laser hardening, electron beam hardening, or there can be thermochemical treatments, in which case not only are we affecting the heating the surface, but also we are altering its composition. The important ones in the context of steel are carburizing, nitriding and carbonitriding. So, to summarize this slide, we can have thermal treatments and thermomechanical treatments. Further, of course, we can even envisage treatments involving magnetic fields and other kind of external stimuli, but we restrict ourselves here to basically to thermal treatments. In thermal treatments, we have those treatments which affect the entire bulk or those treatments which affect the surface, focus being on the ones related to steel. Some of these treatments like annealing, normalizing, hardening we have encountered before. We will say a little more about tempering in the coming slides, and we additionally introduce two new terms, Mar tempering and Os tempering. Annealing itself comes in many types, and some of these types are listed here: full annealing, recrystallization annealing, stress relief annealing and spheroidization annealing. Each one of these annealings is especially intended to produce a specific change in the properties and the microstructure. And for instance, in recrystallization annealing, you try to replace cold work grains with recrystallized grains. That means that we will have to understand what is recrystallization, which we will do so in one of the coming slides. As far as surface treatments goes, there are those which affect the chemistry of the surface, like which are called thermomechanical treatments, and these include carburizing, nitriding and carbonitriding. In carburizing, you introduce carbon onto the surface at high temperatures. Nitriding, you introduce nitrogen, and in carbonitriding is a combined process. In thermal treatments, you can harden the material by heating the surface, either using flame, induction sources, that means RF sources, laser or electron beam. So, this is a broad overview of the treatments which you can undertake to change the properties of steel. Now, where are the temperature ranges in which you actually carry out these treatments, and what is the reason, we will see here. Now, typically the range of useful products is, as we have seen, that is around centered around this from low carbon steel, which might start here, to certain high carbon steel. So, we see that there are those treatments which are carried out below the A1 temperature, and these treatments are the spheroidization treatment, the stress relief annealing treatment and the recrystallization annealing treatment. There are those which are carried out above the A3 or the ACM line, like the normalization. So, we carry out normalization in the temperature regime, which is above the ACM line for hypereutectoid steels and above the A3 line for the hypoeutectoid steels. Full annealing, on the other hand, is carried about above the A3 line for the hypoeutectoid steels, like here. So, when you want to do full annealing, you will carry out it in the regime of above A3 for hypoeutectoid steel. However, for hypereutectoid steels, the full annealing is carried out only above the A1 line and not above the ACM line. So, this is the range we carry out. We will see the reason very soon. So, therefore, there are preferred temperature regimes in which these treatments are carried out, and it should be remembered that whenever you are talking about a heat treatment, it costs industry in terms of time. It also costs in terms of capital investment, because you need furnaces in which these material have to be put and heat treated, and further some of these furnaces may be batch type, which means that it can actually slow down your production. So, therefore, optimizing the heat treatment for a desired microstructure and properties is very important. Now, what is full annealing? In full annealing, we heat above the A3 A1 line, like we have seen here. We heat in this regime. So, this is my A3 line above for the hypoeutectoid steels and A1 line above the hypereutectoid steels. We basically carry out a furnace cooling. That means we cool very slow, and you have seen that we get a cooling rate of the order of 10 power minus 3 or so Kelvin per second. Kelvin. So, this is, we have listed all the rates of cooling here for various furnaces, and we saw that we get about 10 power minus 5 to 10 power minus 3 Kelvin per second, which is a very, very low slow cooling rate, compared especially to treatments like air cooling, which itself is a few orders of magnitude faster. And the final product, as we have seen, is coarse perlite, which has not so high hardness, harder than of course a pure iron, but not so high hardness as compared to what we can get by say quenching the steel, but we have increased ductility. We do not carry out this treatment above the ACM. For instance, full annealing is not carried above ACM. This is to avoid a continuous network of pro-eutectoid cementite along the grain boundaries, and we have noted previously, and I will go to the board to explain you why this so, that this continuous network is bad news as far as the properties go. So, for instance, suppose I now slowly cool and you have a polycrystalline austenite at high temperatures, and I do my heat treatment not above A1 but above ACM. What might happen is that, so you have your polycrystalline grain boundary. So, what might happen is that when you slowly cool from above, you will produce a continuous network of cementite along the grain boundaries. Now, the cementite is a brittle phase, a hard phase, therefore, continuous cracks can propagate along these paths, and therefore, the material may fail in intergranular fashion. So, this is my continuous network of cementite along the prior austenite grain boundaries. You have cracks which can propagate along the grain boundaries of the prior austenite, and therefore, your material will have very poor toughness, especially under impact, and therefore, you do not want such a microstructure. And to avoid such a microstructure, what we do is that we carry out full annealing not above the ACM line, but we carry it above the A1 line, which is here. So, this is my range in which I carry out my full annealing. This is my right. So, this full annealing of course produces a microstructure which has very low residual stresses and is good in terms of ductility. Recrystallization annealing, and we will try to understand this term recrystallization in detail later on, and we will see it is not just a phase transformation, it is a term related to microstructure transformation, and typically you would like to carry out recrystallization to restore ductility in a material. Suppose I am cold working sheets, what might happen is that after I cold work, say give a certain reduction, say 20% reduction on the sheet, the material becomes harder because of strain hardening, and therefore, the ductility of the material comes down, and to restore this ductility so that you can further deform the sheets, you would carry out such kind of recrystallization annealing in between process steps. For other reasons also you may want to carry out recrystallization annealing to produce a microstructure in which you have strain free grains. Typically, this is done below A1, and you give sufficient time so that these cold work grains are replaced by new stress free grains. So, essentially you have material at the end which is ductile, where the defect density is small, the dislocation density is small, and the material further can be worked if necessary. So, in recrystallization annealing, which is carried out just below A1 temperature, you have a material finally produced which is also very, very ductile, and this is carried out below A1 for hyper and hypoeutectoid steels. Stress relief annealing is given to get rid of residual stress. Now, where is the temperature regime in which carry stress relief annealing is again it is below the A1 temperature, and you would like to carry out below the A1 temperature, and the reason that you have residual stresses here, the ones we are talking about are not the ones which are associated with typically with microstructural defects, but we are talking about that which is resulting from differential cooling, machining and cold working, and even martensitic transformation we had noted is associated with lot of strains, volume changes. We have already noted the technical term for that is the Bain distortion, and therefore, martensite formation also gives rise to considerable amount of residual stresses in the material, These residual stresses could also come from sources like welding, wherein a pool of material forms and solidifies, and in this process you may have residual stresses forming in the material. These residual stresses, they may be coming from, as we have pointed out, from various sources like differential cooling of in a two-phase material, or a surface cooling at a different rate from the interior, machining and cold working, Martensitic transformation, welding, and etc. So, these are just a few sources, there could be other sources, could be bad for the component. So, what might happen to the component is that the component may warp in service or warp after during the further steps in for instance component formation. Suppose you had a welded component and you want to machine it further, during this step the component may undergo warpage, and therefore, these residual stresses could be deleterious to the material. In an earlier class we had noted that how residual stresses can even be beneficial. So, we should not construe that always residual stresses are detrimental to the material. There could be beneficial effects of residual stress in many circumstances, but here we are talking about the deleterious effects of residual stress and how to get rid of this residual stress via a process known as stress relief annealing. So, this is my stress relief annealing process. So, to get rid of this residual stresses, I heat below A1 as I pointed out, and this leads to a phenomena known as recovery, which we will deal in a little, this is a technical term, and we will talk about what is recovery in little more detail in the coming slides. And during recovery, there is of course, there is lot of annihilation of dislocations and other microstructural defects, but the focus is on the macroscopic residual stresses, which also are reduced, and the material therefore has less chance of warping during further processing steps or during service. So, in this current slide, the important kind of annealing known as stress relief annealing is mentioned, and we would like to carry this out to get rid of the various sources of residual stresses. And here we are not replacing the entire stress free grains, strained grains with stress free grains, but we are trying to locally rearrange the stresses, so that the final product is low in stresses, which can lead to reduce the warping. Now, sterilization annealing is specially carried out not in all kinds of materials, but it is carried out in high carbon steels requiring extensive machining prior to final hardening and tempering. And in this there are cementite plates, and these cementite plates as we have pointed out, cementite is a brittle phase, we replace with cementite in the form of spheroids. So, initially you may have an cementite which has this morphology of plates, and we try to replace this with a morphology which is more like a sphere, and in this process we are increasing the ductility, because these plates corners can act like stress concentrators, and in the form of sphere such kind of stress concentration does not take place, and therefore, if you are doing this spheroidization annealing, these cementite plates can be replaced by cementite spheroids, which increase the ductility of the material. So, as I pointed out, this is typically done in high carbon steels requiring extensive machining prior to final hardening and tempering. The reduction in surface energy or the interface energy is responsible for this, because if you look at a plate, the interface energy per unit volume for a plate, interface area per unit volume, which also translates into interface energy per unit volume, is larger as compared to that for a sphere, which has a least interface energy per unit volume of the material. Therefore, using this reduction in interfacial energy as the driving force, we can carry out ferrodization annealing to increase the ductility. This is typically done, as we saw before, above A1, below or above A1, but for a long period of time. So, this requires a long time, because this process is very slow, and unless extremely required, this kind of a process should not be carried out. Now, the next term we have already noted is what we call normalizing, and we had referred to normalizing again like full annealing in the TTD or CCT diagram. So, we had noted that normalizing is such a kind of treatment in which you produce, you cool at a rate such that it intersects the pearlitic curve, and the product is typically pearlite, fine pearlite, as compared to some of the other processes which involve either higher or lower cooling rate. So, in normalizing, you heat above A3 or ACM for hypereutectoid steel, A3 for hypoeutectoid steel, and you cause austenization, that means the starting product is gamma. Then, as we have seen, that you do air cooling, and air cooling produces fine pearlite, with high hardness. The purposes of normalizing is to refine the grain prior to hardening, to harden steel slightly, or to reduce segregation in castings and forgings. So, there are multiple purposes for which normalizing is used, but the final microstructure is fine perlite. And in hypoeutectoid steel, the normalizing is done 50 degrees above the annealing temperature, while in hypereutectoid steel it is done above the ACM. In this case, again we might wonder that why is that. Previously I had pointed out that there could form a continuous network of, we have seen that it forms a continuous network along grain boundary, the cementite. So, in this case also we are taking the steel above the ACM temperature and cooling. So, why is not that this continuous network is a problem? The reason is that we are cooling very fast in normalizing, unlike in annealing process, and this fast cooling avoids this continuous network of film along the grain boundaries. So, therefore, in normalization process in which involves faster cooling, we can actually heat above ACM before we start our cooling. And so, to summarize what is this normalizing process, we start with heat the substance to a gamma phase field, air cool it to produce a fine perlitic microstructure which has a higher hardness as compared to, say, for instance, coarse perlite, but definitely lower than martensite as we have seen before. This process can be used to refine the grain structure prior to hardening, to harden steel slightly, or to reduce segregation in castings and forgings. This could be a problem, for instance, suppose you are casting a very large amount of material, there could be some segregation, and this can be reduced. Now, we take up this process hardening, and we have already noted that to produce hardening, we need to produce the microconstituent node or the phase called martensite, and we already seen that this formation of martensite involves this Bain distortion, and we have understood it via the invariant plane strain construct. Now, we already know that we have to heat it above the A3 or ACM temperature. So, above the A3 or ACM temperature, so that we can get a full gamma, and after this gamma is produced, we quench to avoid the nose of the CCT diagram, which is, that means we have to cool it at a critical rate, and so that we can produce martensite in the microstructure. This quench process produces residual stress strains in the material, and further we have to note that this transformation to martensite is usually not complete. That means, we will have a certain amount of residual or retained austenite. We also noted that martensite is hard and brittle, and therefore, we have to give a tempering operation immediately after hardening, so that we have a good combination of ductility and strength. Now, an important point in this context is that suppose I have a cylinder and I quench it in a medium. Suppose this is my bath having water, and I put it inside this water bath. So, this is water bath at room temperature. So, this is a gamma and this is the hot. Then it is obvious that suppose this is my body and this is my quenching medium. Then only the surface of the quenching medium, which is this part. Of course, if it is in a complete bath, then all the surfaces will feel the effect of the quenching medium. That means, immediately the heat from here will be withdrawn from the surface area, and this will immediately be cooled down to the temperature close to that of the quenching medium. However, even if you quench this surface very fast, the interior of the material, say a point X in the material or a point Y in the material, these points are not in direct contact with the material, with the quenching medium, and therefore, the way that this point X is going to be cooled is via conduction. That means, heat has to flow to the surface and has to be removed. Now, this obviously depends on the thermal conductivity of the material. So, this depends on the thermal conductivity and not merely a function of the what we might call the effect of the quenching medium. So, the point y for instance might actually you may draw heat towards this surface and some of the heat may also flow to this surface, but essentially the interior points within the cylinder, say which could be located somewhere here or here within the cylinder, those interior points within the cylinder do not feel the direct effect of the quenching medium, and they are dependent on the thermal conductivity of the material being quenched, and therefore, they do not face such an severe cooling rate as the surface faces. So, what is the consequence of this? What is the consequence of the fact that now only my surface is feeling my quenching rate? So, what might happen is that if you take a thin enough cylinder, so this is the first example I am taking a thin enough cylinder, for instance this is about half an inch in diameter, and the point x in the middle for instance is not too far away from the surface, so which is S, and therefore, heat can quickly be conducted away, and overall the material feels a reasonably high cooling rate, and therefore, if you plot the hardness you will see that the hardness dips a little bit, but the hardness on the surface is not much lower than much higher than the hardness on the interior, which is at a point x for instance. Now, if I make the cylinder diameter larger, then the point x for instance in the middle feels a lower cooling rate as compared to that x1 which is here. So, the x2 feels a lower cooling rate, and if I keep on increasing my diameter, a point in the center which is x3 feels an even lower cooling rate, and if I increase the diameter to say 1.5 inches. So, here the x4 will feel a even slower cooling rate. So, I can write this down as T x1 dot is higher than T x2 dot is higher than T x3 dot is higher than T x4 dot. Even in the case for instance, suppose I take a thick cylinder, the regions close to the surface are feeling a high cooling rate, but not the points close to the interior. Now, what happens? That means that suppose I take a 3/4 inch cylinder or a certain larger cylinder. So, if this diameter is say D1, which is in this case example is half an inch, but could be any number, and this is D2 and this is D3 and I have a D4. So, what happens is that with increasing diameter, so I have my increasing diameter, the interior of the material, the central point which is marked as x, feels a lower and lower severity of the quench. Therefore, the hardness of such a material keeps on decreasing toward the center, and there comes a point where I produce only 50% martensite at the center. So, the remaining 50%. So, what happens is that, so I can see this schematically in this diagram. So, if you have a thin enough cylinder, I produce full martensite, but if I increase the thickness of the cylinder, I produce a combination of perlite and martensite. Now, this combination of perlite and martensite, because the untransformed, so this combination of perlite and martensite is not as hard as my full martensitic structure. So, this arbitrary cutoff where I produce 50% martensite and 50% perlite is called the critical cooling rate to which I need to cool my, which is for instance here the critical cooling rate, such that throughout the section I at least obtain 50% martensite. So, suppose I have a diameter which is, say for instance in this example the critical diameter is 1 inch. If I take a diameter which is to the left of this, so I choose a diameter which is smaller than the critical diameter, then I would obtain more than 50% martensite, and if I choose a diameter which is to larger than the critical diameter, then there will be lesser amount of martensite, in fact there will be more of perlite. And if there is less amount of martensite, then you would notice that the hardness at the center is even below that which you have obtained for the critical cooling rate, and therefore, the hardness falls toward the center. Now, such a material as you can see has not been through hardened. Truly a material which has been through hardened is, for instance, this example in half an inch material, as you go from on increasing the diameter, the hardness falls at the center, but you do tolerate about 50% martensite, which you call a critical diameter, at which if you cool, then you at least have 50% martensite to give you some amount of or the requisite amount of hardness, but diameters larger than 50 this critical diameter would have at the center hardness even lower than that for the critical diameter, and wherein you obtain more perlite than 50, and that means it is less than 50% martensite here in this regime of the sizes. So, you have here in this range of the diameters, that means you have now a sample in which you have a central core. Say for instance, suppose I am talking about a cylinder which is long in this section, that means I have a central core which I am shading here, and this central core does not have even 50% martensite and therefore, is soft as compared to the surface, which of course, has felt the full severity of the quenching medium and therefore, is 100% martensite. So, therefore, I can only harden that much through sections by quenching, which is for instance, below the critical diameter. That means, you are now placing a limitation on the amount or the thickness of the sections which can be hardened. Of course, the geometry of the specimen need not be cylindrical, it could be plate like, but again if you are using a plate like specimen, which of course you are seeing a cross section here, then you would note that if I choose a plate which is more than the critical thickness, then what will happen is that there will be a central core region which has less than 50% martensite and therefore, has not been through hardened. Now, this can be understood using CCT diagrams, as in a single diagram. Now, we are drawing multiple cooling curves. Now, these multiple cooling curves are not for different methods of cooling. For instance, earlier we had seen multiple cooling curves, wherein we said that I am doing full annealing inside a furnace once, I may be doing normalizing, that means cooling in air. Third case, I could actually be cooling in by quenching in oil, etc. But in this case, we are actually quenching this material in say a cooling medium like water. Of course, I keep the conditions constant, like for instance, I just quench it into water, I do not vigorously shake it or anything. Then I note that the surface could be cooling at a rate as shown by the red curve. So, this could be my curve which is representative of the surface which is forming full martensite. So, this curve could be the one which is for the surface. And this point could be for just below the surface, and this point could be at the center of the cylinder, for instance. Now, alternate way of thinking of the same curves is that I can think of this as a material which is having a certain diameter, say D1, and for instance, this critical cooling we have noted is a diameter which is D3. So, for critical cooling rate, this will be a diameter D3, and this could be thicker diameters like D4 and D5. So, now we have extended the utility of the CCT diagrams by drawing cooling curves not for different cooling treatments, but for either different diameter cylinders or specimens with different thicknesses, or tracking the cooling at different points within a thick specimen. For instance, the surface could be feeling a very high cooling rate, while some point in the interior could be feeling, for instance, just the critical cooling rate, in which you will form 50% martensite, or somewhere deeper in the material you will just get fine pearlite. That means, there is a microstructure variation within the sample while you are quenching the sample, and that means that we have to be little careful that whenever we dealt with CCT diagrams, we had talked about quenching and producing martensite. What essentially we were talking was that the sample surface is forming martensite, not the entire sample. Of course, we are talking about a slow cooling treatment, the entire sample is in equilibrium, and therefore, you are getting, say for instance, coarse pearlite, then the entire sample will be coarse pearlite. But in the context of quenching, we have to be a little careful that even though my sample surface is getting quenched at a very high rate, and therefore, I am producing full martensite, the sample interior could be left with the only pearlite or fine pearlite. That means that there is a variation in microstructure from interior outside to interior. So, now I cannot draw any uniform microstructure. So, there is a and needless to say, such a variation in microstructure produces resultant changes in the hardness, for instance, and other properties. Of course, measuring other properties in individual sections may be difficult, but hardness is easy to measure. We can put an enter on the surface, close to the surface. When suppose I made a cylinder and I quenched it. So, what I can do is that for such a cylinder, I can put an indenter at this point, close to the surface, take it slowly, put various indentations at various points, and therefore, measure the variation in hardness. And such a plot has been, as you have seen before, shows that the hardness from the surface falls towards the interior. So, therefore, now I need to worry about the fact that if my sections are very thick, there is going to be a variation in microstructure, and therefore, there is going to be a variation in properties. That means, there is no uniform properties that the material will have, and whatever tensile properties you measure would be an average. Sometimes this may be beneficial, because sometimes you would want a hard surface and a tough interior. So, such a treatment would automatically give you such a hard surface and a tough interior, but then understanding the behavior of or deformation behavior of such a kind of a microstructure could be rather difficult. Now, this is one of the motivations, as we shall see later, to produce what we call alloy steels, so that my CCT diagrams are moved towards the right. That means, in alloy steels you will note that the nose of the T diagram, which is typically, as we have noted, this nose is of the order of just a second. That means, the quenching rates you need to employ are very, very large. But suppose you are able to move the nose of the TT diagram to the right, that means that I can apply less severe quenching rates to produce martensite. Then such a material not only will be easily hardenable, hardenable being the ability to harden with the least severe quench. So, I will repeat again that hardenability is a technical term. It is the ability to harden a material by producing martensite via the least possible severe quench, and that is one benefit of moving the TT diagrams to the right, and that can be done via alloying, as I pointed out, but additionally also the thermal stresses produced in the material are also going to be low. Now, we said while we talked about quenching that actually we have various severities of quench well within a class. For instance, suppose I could be talking about quenching in water, but that does not represent a single quenching rate, but actually could represent multiple quenching rates. Now, the various quenching process with an severity of quench as measured by a value called the H value. The H is defined, or the H or the severity of quench is indicated by the heat transfer equivalent of H, which is given by H is given as F by K, where F is the heat transfer factor and K is the thermal conductivity. In other words, H measures that how efficient is a quenching medium in removing heat, and ideal quench is considered when you have the H value of infinity. That means that is the perfect you would like to aim. Any other process would have a H value which is lower. Air quenching with no agitation gives you H value of 0.02. Oil quenching with again no agitation can give you 0.2 cooling rate, that means it is a faster cooling rate. If you use slice agitation, the H value increases, that means now you are extracting heat better from the material by agitating it slightly. You can also do increasing amount of agitation to obtain a H value of 0.7. This implies for a single quenching medium like oil, you can actually obtain a range of cooling rates, or what you meant is the cooling rates being indicated by the H value, by actually either holding the sample still or by actually agitating it at various rates. Now, a few points have to be noted in this regard. That means that apart from the nature of the quenching medium, the vigorousness of the shake determines the severity of the quench. That means I can increase the severity of quench by shaking the material. When a hot solid is put in a liquid medium, gas bubbles form at the interface of the solid. This may happen, and this gas bubbles which are present at the interface with the medium can actually deteriorate the heat extraction process. This is because the gas has a poor thermal conductivity, and therefore, the quenching rate is reduced locally, especially where the gas bubble is present. Providing agitation, that means shaking in the solid liquid, helps in bringing the liquid medium in direct contact with the liquid, thus it improves the heat transfer and the cooling rate. The H value or index compares the relative ability of various media, that means the listed table we are seeing above, that means gases and liquids to cool a hot solid. Of course, we have already seen that the ideal quench, which is right at the bottom here with an H value of infinity, is a conceptual idea with heat transfer factor of 100 infinity. So, this is an important point to note, that even though I expect a certain medium to cool at a very fast rate, formation of gas bubbles can impede this process, especially very locally where the gas bubble is forming. Therefore, if I agitate the solid or equivalently agitate the liquid, what might happen that the medium can come in direct contact with the substance or the material, for instance steel in this case, and therefore give you a higher cooling rate. Again in the same case with water quench, that if I do not agitate I get a lower H value, while if I vigorously agitate I can get a higher H value. In the case of even oil quench, we have seen that we can actually increase the factor H factor by a factor of 3 or more by vigorous agitation. More than water quench, you can even obtain higher quenching rates by using brine quench. That means you take water in which salt has been dissolved, and we can get a higher quenching rate. And even in brine, if you do vigorous agitation, you can get a H factor up to 5. So, the message of the slide is that often when we talk about water quench or oil quench or even air cooling, we have to specify if the medium or the substance is being agitated, because in this case the overall heat transfer coefficient, that means suppose I am keeping a substance, I am blowing air on it by a fan in air, then I get a better heat transfer coefficient or a better heat removal from the material, and therefore I get a better quench on the inside the material. And I can use different media apart from oil quench and water quench, like brine quench, and to get a better cooling rate, and there are other specialized media also which you can use. Of course, we have to note that in these cases we are assuming that the quenching medium is at room temperature, but of course you can also keep the quenching medium below room temperature. You can even go to cryogenic temperatures. If for instance, if the MF temperature for a certain substance is below room temperature, then you need to cool the substance below room temperature, so that you can produce full martensite. So, these are some details of the quenching medium and the kind of heat treatment you need to carry. The standard test to find out hardenability of a material is via what is known as a Jominy end quench test, in which case you take a cylindrical specimen, you throw a water jet at the bottom. So, this end of the specimen is being cooled by water jet, the other end of the specimen is being only cooled in the open air. So, all the heat which is being extracted from the bottom, therefore, the heat has to flow from top to bottom, from in other words, so heat has to flow in this direction. So, this end of the specimen directly feels the quenching medium, while this end is only being air cooled, and therefore, heat has to flow from top to bottom and be removed by this water jet. Now, such a quench produces martensite on the surface of this material. So, if you compare this and suppose this is my x point and this is y point. So, wherever this x is, you have high hardness due to presence of martensite, while the other end y is low in hardness, because there you only are producing perlite. And you would like to know where you produce 50% martensite, and this you can do by actually cutting the specimen and polishing it. So, what you can do is that you can take your cylindrical specimen. So, this is my cylindrical specimen. So, I remove a certain section from the top, so that I have a flat top, and now what I can do is that I can measure my hardness from, say, this is my quench end, which I have marked as x, and I can take hardness at various points along the cylinder, and I can plot it. Further, I can also see using my metallographic studies that at which section am I producing, for instance, 50% martensite. So, by using a combination of hardness and metallographic studies, I can find out the variation in hardness and also locate the region at which I can get 50% martensite. So, this is how the plot of the hardness is expected to look. You have a decrease in hardness along with the change in microstructure, and at certain distance you can actually produce 50% martensite. We are not considering the details of this Jominy end quench test, but this can also tell you how hardenable the material is. A more hardenable material you can actually harden to a larger distance as compared to a less hardenable material, because as we have pointed out that the heat transfer from a section somewhere here is dependent on the heat thermal conductivity towards the bottom. That means, the heat is being conducted through the material and is not in direct touch with the quenching medium. As I pointed out, this quenching treatment has to be followed by a tempering treatment, so that we can get a combination of ductility and strength. That means, we can optimize strength and toughness being the area under the curve in a tensile test, or suppose you are wanting to do an impact test, then it is the energy absorbed during impact. So, during the tempering process, the body centered tetragonal structure of martensite, which is represented as alpha prime, tends to go back to its equilibrium state, and the equilibrium being given by the phase diagram, because this alpha prime is a metastable state. The equilibrium phases being alpha and Fe3C, Fe3C being orthorhombic, alpha being BCC, that means a solid solution of carbon and iron. So, you have a product of ferrite and cementite when you temper martensite. Of course, you do not allow all the martensite to be converted into ferrite and cementite, you only do it so as to get the optimum combination of strength and ductility. So, you heat below the eutectoid temperature and wait, and then after that slowly cool the sample. The actual microstructural changes taking place during this tempering are very complex, and we are not considering them in detail here, but certain specialized texts in this area would help you. Tool steel, for instance, as quenched is about 65 RC, but we can temper it to get a RC value, which is a Rockwell C hardness value of about 45, so that, or 55, so that this can be used in actual service. So, typically hardening processes are followed by tempering process, so that you can get a combination of ductility and strength. There are certain variations of this process which can actually give you certain benefits with regard to residual stresses, and the two important processes which are used, one is called Mar tempering, other is called Aus tempering. Now, of course, we are using a single master curve to study all this, but we have to note that since this also involves cooling steps, this is an extension of the standard TTD diagram. Now, we do Mar tempering to avoid residual stresses generated during quenching. Now, what we do is that we austenite steel is quenched just above MS. So, we take the steel, austenize at high temperatures, then we cool it along the red line. Actually, the red line is overlaid on the blue line. So, for now we will focus on the red line. We hold it, bring it down just above the MS temperature, and then we allow the sample to homogenize in temperature, because when we do a normal quench, for instance, suppose I take a cylindrical sample and quench it, the surface faces the quenching medium, and that means that this is cooled and the interior is not cold, and in this process residual stresses are generated. These residual stresses are the thermal residual stresses, which is in addition to the residual stresses produced directly due to the transformation itself. So, after this temperature homogenization hold, which is from here to here, so that I hold it, so that my entire sample is now homogenized at temperature, and now of course, the sample itself is pretty cool, and from here I quench now to cross the martensite start and martensite finish lines, so that finally I produce a martensite uniformly across. And this is important because the steel is now quenched such that the entire sample transforms simultaneously. So, there is a slight variation in the quenching process, and this heat treatment cycle now involves a quench regime. Say for instance, I can label this XY. So, I start from the X point, quench it to Y point, then I go to Z, and then quench it to room temperature. So, therefore, during the XY I am cooling it to avoid the nose of the TT diagram, then I hold it above the MS temperature, so that still we are in the gamma phase field, but we are not allowing any transformation. What we are allowing is that the entire sample is brought to a same temperature, and then further we quench it, so that the residual stresses produced in the martensite are small, and that implies that the cracks, quench cracks which are produced, this residual stresses which is building up in the material is small, and which is good for in service applications. So, finally, of course, we quench the material from Z to R to produce full amount of martensite. In Aus tempering, which is another variation, and this again is designed to avoid residual stresses generated during quenching, the austenized steel is quenched above MS, again like before we follow the XY part of the curve. Then we do not, then after crossing Z we do not quench, but we hold it isothermally so as to produce a final microstructure which is bainite. So, in the Mar tempering process we are producing martensite and avoiding residual thermal stresses. In Aus tempering we are again holding the austenite just above the MS temperature, but isothermally holding is to finally produce the bainite, which is, as we know, since we are now working at very low temperatures, we know that it will be a very fine bainite which is produced, and which will be which will have reasonably good strength and which is good for applications. So, now we have considered two variations of the quenching process, and these two have been designed specifically to reduce the residual stresses which arise during quenching. One is Mod-tempering, another is Aus-tempering. And also we have seen that how the TTD diagram can be used as an important engineering application to design these heat treatments, specifically the ones we have just now seen. So, where we have used a specific shape of the nose, that means we avoid the nose, but then we know that there is more time available below the nose. So, I can hold my sample in this regime, which is I am shown by the circle, and therefore, the precise shape of the TTD diagram is being used to design my heat treatment, so as to produce a product which is not only is hard, but often has a combination of hardness and toughness, but also is low on residual stresses which could lead to warping. Even in the case of martensite, it is needless to say we would like to do some tempering later on to increase the overall toughness of the material. Now, the next topic we would like to consider is alloy steels,